What changes? All we've done is disconnect the battery.
Voltage.
How will the voltage change?
No voltage.
How will it change? You're saying it won't change?
No, it will, there just won't be voltage.
We can't divide by 0, right?
Well, the charge stays the same.
All right, so this is 3/2 Q sub naught.
Well, there's just no circuit, so the potential, the difference in potential should just stay the same. Because none of it could have gone anywhere.
Yeah, so we do maintain the charge, that's the big thing. Once you disconnect, charge will stay charge is now constant. However, we haven't done anything else, all we did is disconnect the battery. So charge stays the same, my capacitance, I haven't changed anything with configuration, so that's still the same. And if those two are the same, that's gotta be the same. All right, anything changing?
The plate should be the same, the electric field of the plate should be the same.
All right, because my charge hasn't changed.
So should the total,
Say total's the same? Because my distance and my voltage stays the same.
which then means the dielectric system.
All right, so disconnecting the battery doesn't change anything. It's what happens next. I'm now going to make D go to the original distance. It's still disconnected.
Charge is still the same.
Area is still the same. All right. We assume that the dielectric changes accordingly.
So the capacitance would be 3. Voltage and a half. Or hold on.
Well, if we're gonna assume that
All right, PJ, you started a sentence, I didn't hear you finish. Then you started on something that looked like you changed your mind. Sounded like you changed your
I
mind.
was checking.
it would be 9
Say this would be 9/2. Going back to the drawing board. Okay.
Wait, how is the capacitance 3?
Because if you look at the formula here, kappa is 3 and D is back to what it originally was.
No, the voltage would be
Half the original,
yeah.
which I think is what you originally
Yeah,
said.
just,
Looking at this equation here, I have 3, this is by 3, that's 3/2. This has to be 1/2. All right, what else? Anything else staying the same or changing? Well, yes, there's the answer to that, but we got our electric fields.
stay the same, the total. Because both the distance and the voltage were halved.
All right, voltage is half. I guess distance is D.
Well, they were.
So if the voltage is half the original, D is the original, E would have to be half the original. So the total would stay the same. Yeah, I'm looking at the last equation. My charge is 3/2, the original kappa is 3, threes would cancel out, and I'm left with half. Right.
And then the plate would stay at 3/2.
And the dielectric,
Stay the same.
all right, there's a master set question that deals with this. Also, another variation of this, because I get bored writing these. What would you do? How would you start out with the initial value. I want to double the voltage, but keep the electric field the same. Is it possible? How would you do it? So it went to V naught and the electric field total. Does not change.
If you disconnect the battery and then half the distance.
All right, so first off, if you want to change the voltage, you gotta disconnect the battery. All right, so if you disconnect the battery, so now V naught is free to change. If you cut you said,
Distance in half.
cut the distance in half, that will double the capacitance. So we have 2C sub naught, so D, 1/2 D sub naught. So you disconnect. And so that's what your suggestion is, so we double the capacitance. We double the capacitance, we are. Else will change. So disconnecting does nothing. So we've got V naught, Q naught, C naught, E naught, E naught, 0. Disconnecting keeps that the same. If we cut the distance in half, my capacitance is twice the original. Q's gotta be the same. So the voltage would be half the original voltage. Because the voltage is Q divided by C. And C got doubled, so voltage gets cut in half.
So then would it be doubling the distance?
So if we double the distance, which is what we did over there, but doubling the distance, we disconnected first, that's the difference between those. So if we disconnected, so Q naught now is constant, we double the distance, this is 1/2 C, and this is 2 V naught, left with the electric fields. Well, what will happen to the electric fields? From the plate?
But the distance and the voltage are doubled, which means the electric field total would stay the same.
Yeah. Also, from this point of view down here, there's no dielectric, so these would be equal to each other. Epsilons of naught, A, and Q all stay the same, so electric field will stay the same. And then you can make this more difficult by saying, I want the voltage to double, electric field and the capacitance to stay the same. Which, well, you definitely, that'd be tricky. There's one of them that I've done that was impossible. I think we will end it with some calculus. I think that just feels right. And hopefully we won't lose Sarah. Any questions before I move on? So if I have a cylindrical capacitor, what was R sub I for inner and R sub O? Wrong way. If it is a capacitor, then whatever charge I have on the inside, I've got the negative on the outside. So let's just say the charge here is Q and the charge on the outer side is negative Q. The outer cylinder is hollow, so this is empty space in this region right here. So basically you have a cylinder inside another cylinder, inside an annular cylinder. And what I want to know is, what is the capacitance? I know that the capacitance is equal to that charge over the change in potential. Q is sort of given to us, C is what we're trying to find, delta Q is where, or sorry, delta V, as people call it today. Delta V is where the real work is. Once we find delta V, we just pop it into here and simplify. Well, oftentimes in something like this, the simplest way is to go back to the relationship between voltage and the electric field. I can't use the simplified forms over there because the electric field is not constant. And so I guess the big question is, what is the electric field coming from this cylindrical core? If it helps, it was on the chapter 24 flash quiz. Apparently it doesn't help.
Like the formula?
Yes.
It was like the volume charge density times the inner, or the outer radius minus the inner radius over, never mind.
All right, since we are outside of this right here and exploiting symmetries, we can treat this as a one-dimensional line, since we're in this region out here. Or if we're looking at it head-on, we're in this region. All right, you don't know it? Let's do this. We come up with a Gaussian surface. I know that my electric flux is equal to Q enclosed over epsilon sub naught. My electric flux, I know that my Gaussian surface is a cylinder, but from symmetry point of view, my electric field is going to be going away from the central line here. I'm assuming we have a really long cylindrical cylinder here. So my electric flux is only through the sides of my cylinder. So this is E, A, oh, sorry, erasing that, equals, well, electric flux, let's E dot dA, go ahead and go whole hog, is equal to my enclosed charge. Well, my enclosed charge is whatever my density here is times the length. So I'm gonna use linear density here because again, I'm treating it like a single line. If you wanna do volumetric density, well, R1's gotta be a conductor. So all the charge is gonna be on the outer surface. But I'm gonna let lambda be Q over L, where L is this length. Side view, L is the distance in. So that is going to be lambda times L divided by epsilon sub naught. E dot dA, well again, my electric field is perpendicular to the surface everywhere. So that's just gonna be the integral of E dA. The magnitude of my electric field is the same everywhere around here because of symmetry. And so this is just E dA. It's just EA. So this is the electric field strength times my area, which is 2 pi R L is equal to lambda L over epsilon sub naught. L's go away. And I'm left with, well, we got the 2 pi over there, so my electric field is equal to lambda over 2 pi R epsilon sub naught. That's my electric field strength. It is in the radial direction. So where that's the center, and so that's the direction of my electric field. So my voltage is the negative integral of E dot dr, which is the integral, the negative of the integral of, there's my E. I'll go ahead and stick it inside, lambda over 2 pi epsilon naught R dr. My radial, since my radial vector is pointing outwards, dr is also pointing outwards, same direction as my electric field. And so I can drop my dot product, just go straight to that. So this is negative lambda over 2 pi epsilon sub naught, integral of dr over r. I now have a single variable. By limits of integration, well, from r inner to r outer. This is the section here that we're concerned about. Actually, yeah, that's r inner to r outer. And what's the integral of dr over r?
Two-thirds r to the 3 over 2 power.
No. What were you doing there?
R would be to the power of -1.
Right. So r to the -1.
Plus 1 would be 0.
And then you divide by 0?
I don't
Would it be ln r?
Yeah, it's the natural log.
know. Okay.
So we end up with lambda over 2 pi epsilon sub naught, natural log r naught over ri. Negative. we don't like the negative, we can adjust that, so that's lambda over 2 pi epsilon sub naught, natural log of Ri over R sub naught. Let's see if this makes some sense here. I know that Ri is less than R sub naught. So this right here is a fraction that is less than 1. The natural log of something less than 1.
0.
Yeah. The natural log of 1 is 0. The natural log of something less than 1,
It's negative.
negative. So this whole thing right here is negative. I assumed a positive core, so that's a positive number. Epsilon sub naught's a constant positive. So I got an overall voltage of negative. Well, I know that my voltage decreases as I move in the direction of the electric field, and since my electric field is moving outwards, my voltage from here to here, from R inner to R outer, would indeed be negative. So the fact that we would have a negative answer here matches what should happen. We haven't actually finished the problem, because the problem's asking for what is the capacitance. And so my capacitance is equal to Q divided by that, so that's Q 2 pi epsilon sub naught over lambda natural log Ri over Ro. And so if the cylindrical capacitor is truly infinitely large, well, we have an infinitely large capacitor. And as with any of these things, it comes down to at what point can you consider, yeah, that's close enough to an infinitely long